This video will give you the procedures needed to design a distillation tower, calculate the energy required to operate the tower, also to determine the total cost of the equipment, and then come up with a capitalized operating cost for the tower. We're going to use an example here on the distillation tower where we're going to separate a feed containing methanol and normal propanol. The total feed flow to the distillation column is 100 moles per second. The concentration of the methanol in the feed is a 0.25 mole fraction, and the feed to the preheater is 25 degrees Celsius. Our target distillate composition will be a 0.90 mole fraction of methanol, and the bottom's target is 0.035 mole fraction methanol. And this particular tower is running at 1 atmosphere pressure. We wish to determine the tower height and diameter, how many trays are necessary to achieve the separation, what the areas of the preheater, reboiler, and condenser are, what the installed cost of all the equipment will be, the annual operating cost for utilities, and then the total capitalized cost using a 3.5% interest rate and a 10-year plant life. As an overview, here's a generic column that has N stages plus a reboiler, which will also act like an equilibrium stage. With our feed at 100 moles per second and our feed composition and target distillate and bottoms composition, a simple material balance will show that the distillate flow leaving the top of the column would be 24.86 moles per second, and the bottoms flow will be 75.14 moles per second. As a review, let's take a look at the various operating lines and Q lines for a column. The upper operating line equation is given where the mole fraction in the vapor phase is equal to the distillate target mole fraction over R plus 1, where R is the reflux ratio, plus the mole fraction liquid phase times R over R plus 1. We also have a Q line equation given here, where it's going to be a function of the Q, which is a property of how we wish to introduce the feed into the column, and the feed composition, which is labeled as Z sub F. And lastly, we have a lower operating line equation where the mole fraction in the vapor phase is equal to the mole fraction in the liquid times RB plus 1 over RB, and RB is the boil-up ratio, minus XB over RB. You may wish to write these equations down and pause at this time. We will be returning to this slide frequently in the explanations. Also note that what the slopes and intercepts are for this equation, because this will appear quite often in this presentation. Now, all three of the lines that we specified in the previous slide all intersect at the feed stage. And so the point where these three lines intersect can be calculated by setting the equations equal to each other. In this example, I took the upper operating line equation and the Q line equation, and since they intersect each other, we wish to find out what's the mole fractions of where that occurs. So I set the two equations equal to each other, and then through some algebra separated the X away from all the other parameters, and the point where it intersects on the X-axis is given by the equation at the bottom. In our particular example, we're going to choose a reflux ratio of 7.0 and a Q value of negative 0.5. This would be a vapor above the dew point temperature of this stream. So we plug in those values into the equation for the intersection, and we will find that the Q line and the upper operating line, they intersect each other when X is 0.1 and Y is 0.2. Now that we know that point of intersection, we can substitute those into our equation for our lower operating line. And since X and Y are known, we can solve for the value of the boil-up ratio, R sub B, and in this case that would equal 0.651, and we'll use this value later on in the presentation. With the reflux ratio and the boil-up ratios known, we can determine the vapor flow rate above and below the feed stage. Above the feed stage, the molar vapor flow rate is given by D times R plus 1, in this case 198.84 moles per second, and below the feed stage, V prime is just RB times B, and that is 48.89 moles per second. In this slide, we have plotted the equilibrium curve along with the upper, lower, and Q lines. And also directly below it, we have the temperature versus mole fraction plot, and we'll see where that can be useful. So knowing what our feed composition is, we can then look at how many stages that we need for our particular column, and we would number from the top to the bottom. Notice on the 5th stage we transition from the upper operating line over the feed stage, and then 7 stages would make up our column. This would include 6 actual trays, and the 7th stage would be our reboiler. Also, let's look at one feature on this that will allow us to determine the temperatures of each individual stage. If we look at the point on the reboiler, the last stage, stage 7, and we know that the mole fraction in the vapor phase is approximately about 0.08. If we take that over to the y equals x line, as you see in gold, and then project that down to the vapor line in the bottom graph, we will find that that intersects at around 95 degrees Celsius or 95.5 degrees C. Likewise, our feed stage can be projected over, and we'll find that the temperature at the feed stage is 93 degrees C. So we can easily find what the temperature is on any particular stage by projecting down. Now we wish to determine the tower diameter. And to do this, we need to find out what the volumetric flow rate is in each section of the tower. With the reboiler section, the temperature is 95.5 degrees C, and we know what the vapor flow rate is based on the lower operating curve parameter R sub B of 48.9 moles per second. And we're going to use the ideal gas law to take a molar flow rate and convert it into a volumetric flow rate. At this temperature and 1 atmosphere of pressure, we will find that we are operating at about 1.48 cubic meters per second. For the feed stage location at temperature equal 93 degrees Celsius, the volumetric flow rate of the feed can be determined at those conditions at 5.97 cubic meters per second. So we can see that the volumetric flow rate is much higher above the feed stage than below the feed stage. And so we want to design our column based on the highest possible flow rate, in this case 5.97 cubic meters per second. We know that the maximum velocity we can have in our column is 0.6 meters per second. And the volumetric flow rate is just equal to the maximum velocity times the area. And so we can solve for the area of our tower by dividing the volumetric flow rate by that velocity, and it turns out to be 9.96 square meters. And using the formula for the area of a cylinder, we can determine that the diameter of our column should be 3.56 meters. And this will have a diameter such that the velocity will never go above 0.6 meters per second. Now we can look at what the cost would be for our particular tower. Since we have 7 total stages from our equilibrium curve, the last stage being the reboiler, the total number of trays in our column would actually be 6. and the tray spacing is 0.6 meters. And so our total height would be given by the 6 minus 1 times 0.6 plus 2 meters, which is air distance above and below the top and bottom tray. So our total height will be 5 meters tall. To determine the cost of the tower, we just need to know the mass of the metal for it, which is given by the perimeter of the column times its height times the thickness of the metal times the metal density. The thickness is given in the original worksheet given to the class, and for a 3.56 meter tower, a thickness of 12 millimeters is appropriate. And if we're using a steel for our vessel material, which has a density of 7,700 kilograms per cubic meter, the total mass of our tower would be 5,167 kilograms. Plugging that into our cost formula, we will find that the cost for this particular vessel is around $38,500. For our trays, we have 6 of those, and knowing the diameter of the tray, we can calculate the cost per tray. And substituting that into the appropriate equation, we would find that the cost of the trays would be $19,450, and the total tower cost, not including the reboiler, condenser, or preheater, is slightly less than $60,000. In order to properly size the feed preheater, we have to do some energy balances around the feed stage. At our feed stage, we see the composition is a mole fraction in the vapor phase of 0.22 and a mole fraction in the liquid phase of 0.08. And the vapor of the enthalpy leaving the feed stage is given by the summation of the individual mole fractions times the specific enthalpy of the vapor, and likewise that would be the same for the liquid. In terms of the specific enthalpy of the liquid, we would use the integral of the heat capacity from a reference temperature to the temperature at that stage, and we integrate that between those two temperatures. For the vapor phase, we would do an integral of the liquid heat capacity from the reference temperature to the liquid's boiling point, plus the heat of vaporization, plus integrating the heat capacity of the vapor from the boiling point temperature to the system temperature T. At 93 degrees Celsius, the specific enthalpy of methanol in the liquid phase is calculated to be 5.8 kilojoules per mole. Methanol in the vapor is 38.9 kilojoules per mole. And the propanol is 9.7 kilojoules per mole for liquid, and the vapor is 49.7. And so we'll find that the liquid mole fraction enthalpy is given by its mole fraction times the specific enthalpy of that, and then we would do the same for the vapor as well. Now we're going back to our definition of what the Q in the Q line actually is, which is the ratio of the enthalpy of the vapor minus the feed enthalpy divided by the ratio of the vapor minus the liquid enthalpy, and we determined those values in the previous slide. We can rearrange this equation so that we can determine the enthalpy of the feed is just equal to the enthalpy of the vapor minus Q times the difference between the enthalpy of the vapor minus the liquid. Using the numbers we just calculated, we would find that the enthalpy of the feed is 66.24 kilojoules per mole. If we use a reference temperature as our inlet temperature, which was done at 25 degrees C, we'll find that the amount of energy the preheater has to provide would be the flow rate of the feed, 100 moles per second, times the difference in enthalpy of the feed leaving versus entering the heat exchanger. And so we will find that the amount of energy required is 6,244 kilowatts. If we're going to use steam at 160 degrees Celsius to supply this energy, we can determine the delta T log mean driving force between the difference between the outlet and inlet temperatures of the heat exchanger. In this case, we're coming out of the heat exchanger at 93 degrees Celsius. We're entering at 25. And we'll find that the log mean temperature driving force is 97 degrees Celsius. We can solve for the area of the preheater by using the energy required by the preheater, 6244 kilojoules per second. The heat transfer coefficient is given to us at 1.8 kilojoules per second meter squared degrees C, and our temperature driving force is 97. This calculates to an area of 35.7 square meters. And using the appropriate coefficients to determine cost, we will find that the preheater cost is given by the equation at the bottom, and it would require approximately $13,142. Now we're going to look at doing an energy balance around the condenser. We have a vapor entering the condenser, and it's being transformed into a liquid at that pressure. And we need to know what are the temperatures of both streams. And we can get this off of the vapor-liquid equilibrium curve and the temperature mole fraction curve. Knowing a distillate mole fraction is 0.9, we can project that value down to our temperature curve and learn what the temperatures of the vapor leaving the top of the column and the liquid leaving the condenser are. In this case, the vapor at the top of the column, where that line intersects the vapor line, we find that to be approximately 71.5 degrees Celsius. The liquid leaving the condenser is calculated to be about 67 degrees C. So now we have the temperatures in and out of the condenser. This will allow us to do an energy balance and therefore calculate the area of the condenser. We can calculate the specific enthalpy of the vapor at 71.5 degrees C, and that's just slightly less than 40 kilojoules per mole. And the liquid at 67 degrees C is 3.76 kilojoules per mole. So the total energy that has to be removed by the condenser would be the total vapor molar flow rate entering the condenser, which we calculated to be 198.84 moles per second, times the change in enthalpy, 39.77 minus 3.76, which calculates to be 7,160 kilowatts. We can use the log mean temperature difference given by the formula in the original handout, and that would calculate to be 31.5 degrees Celsius. Knowing that the heat transfer coefficient for this condenser is 0.6 kilojoules per second meter squared Celsius, and the heat duty and the temperature difference, we can calculate that the total area required by the condenser is around 379 meters squared, and the cost formula for the condenser comes out to be $54,568. Last, we have to determine the size of our reboiler, and so we need to know about the temperature that we have in the reboiler. As we saw before, we can do this by projection of the upper graph down to the lower. And doing it here, we have a temperature of around 95. And so this will be used for calculating the energy balance around the reboiler. Now we're ready to design the reboiler. Based on 95-degree temperature, we can find the specific enthalpy of the vapor and liquid at 49.11 and 9.83 kilojoules per mole respectively. Now the flow of vapor from the reboiler is just given to us by the bottom's flow rate times the boil-up ratio R sub B. And so we can determine how much energy is required to vaporize this stream by taking that flow rate, multiplying it by the change in enthalpy, and that calculates to be 1,918 kilowatts. Now, since the temperature doesn't change in the reboiler, and our steam temperature doesn't change, it just goes from a vapor to a liquid, our log mean temperature difference in the reboiler is just equal to the temperature differences between the two streams, in this case 65 degrees Celsius. So we can calculate the area of the reboiler at 1918 kilojoules per second, divide that by its heat transfer coefficient, 1.8 kilojoules per square meter degrees C second, and divide it by the temperature difference of 65 Celsius. And our reboiler has an area of 16.4 meters squared. So our total cost of our reboiler is approximately $15,360. Now, the costs that we've calculated so far do not account for installation, plumbing, and electrical work, and that is approximately a factor of 3 times the purchase cost. And so the total cost of our plant would be 3 times the individual purchase costs of the 4 pieces of equipment, and that comes out to be $429,000 for our plant. Now we're ready to calculate our operating cost. We know the energy requirements of the condenser, preheater, and reboiler, and we can determine this on an annual basis, where the condenser is removing 225,800 gigajoules per year. The preheater is adding 196,280 gigajoules per year, and the reboiler is using 60,486 gigajoules per year. We're using steam in the preheater and reboiler, and that steam has a value of $13 a gigajoule, so we can determine that the total cost of steam for our plant is a little more than $3.3 million a year. The cooling water in our condenser is considerably less expensive, but it calculates to be $79,900 per year. So our total annual utility bill is a little bit more than $3.4 million a year. But we want to capitalize this cost so that we can compare it with the purchase cost of our distillation tower. And a formula was given to us in our handout for this project, where we would multiply the annual operating cost by a factor, which is a function of the number of years of operation, in this case 10, and the interest rate, which is 3.5%. And the capitalized cost of this plant is $28 million for utilities. Add that to the slightly more than $400,000 for the capital equipment. Our total project is $28,860,000. Notice that the operating cost is the biggest portion of this. And so we ought to design our tower not to minimize its size, but actually to minimize its utility usage. And this can be done by looking at different reflux ratio and different feed conditions.